I want to thank Doss. I think Doss sent me this link, although I've seen it a few times. The guy does do a nice slowdown. Let's start the video with that to my video content. I'm using a slowed down version of it, and no permission needed because it's not the owner. This is not the owner of it. Any rendering compositions from it after it belongs to the owner. It's the way copyright works. All right, so that's my critique of that video that without permission. And here we go with that. I get to critique it, put it online, and because I'm critiquing it, I get to use it. So everyone claims 11 slid off 9. Let's look at 11 push 9 off. It's not going to happen. So and what you're going to see is the deck's going to deflect here and here, the deck and the canopy. You got the workers on the bridge structure now. So, okay, I'm going to stop it there. There's our deflection already. They have you have the failings of 12 of 11 pushing out. We have no indication of any breaks at the nodal area under here. We have indications of this already failed at the bottom with all the photographs of all the cracks. So that's just ridiculous. So this is already leaning back. 12 is leaning at this point now. The redirect is this way, with 12 coming pushing out, and up here we see this leaning inwards. And the reason why is the post-tensioning longitudinal cables are connected to the structure. If you, and I've said this many times, I usually say use a string, but I want you to use a chain now. Use a chain and pull it to a point here, and this is your radius point here. From here and also there. You can then pull a radius point from here to there and here to there. Also a radius point from here to the top of the structure. As it was right here a second ago, your chain would be taking an arc. From this point, it would be arcing over. If this is all connected, then this would also, it's got a little bit of a dip, but it would arc over, and there's the arc. This is now the back part of this little nodule back here, which I'll show in the video, part of the video. A little blister, it's already broken off, I think. And we're going to see that 11 has two members in it of post-tensioning bars. One's at the lower half in the deck, and the other one's outside the deck, going through the deck, if you will, and holding on number 12. And I show that as part of his other videos. Let's go ahead and continue. So now, again, using your chain method, you see that it's taking an arc radius right about there. The arc radius that we're using your chain from this point to here will start rotating. Why do I say a chain? Because at one point your chain is going to push back and your chain will become loose. You'll have too much chain out there. And that explains to you what's going on. That's when it pulls this backwards. We do have to worry about pixelation, things like that in this video. For example, the processor, the computer, the camera sees the contrast of the blue. But when you see the members like this, they're not deflecting, or this is not deflecting. It's that they're on the same plane, and the processor is limited to whatever it is, however much money they got in the processor of this dash cam. And that's why it can't quite determine what it's looking at, so it gives it a shade. So as we look at this, we now have this still on the deck. If you don't run your chain from here is now turned inwards a little bit. Your chain here was here, but your distance from here to here was here on the deck. Now your chain's gotten shorter and it's here now. You've got loose links. That means it's now pulling this apart here to, but number 11 is still acting as a jack, if you will, holding back some of this 12, and this is where it's not quite deteriorated. Number 11 right now has a post-tension bar in the deck. It's now the post-tension bar was from here, visually was from this node to here. You can see where this would now tear apart number 11, if 12 is no longer working at this point, would tear apart the top of this section here on our number 11. And that would look something like, bear with me, so there's that nodal point I was talking about with you. Right here. This is the 12 inside here, right here. It's already deteriorated. Number 11 is at the bottom, but with that much deflection we see in the image, number 11 is now torn up through the top of here, because 11's gone down through the post-tension rod. So here is, the 11 is down here on the ground now on the deck. This is 11. But before, at the point that I'm showing in the video, 11 is now causing this tearing, pushing through all of this material here. And that's going to show again here. Here's 11. It's in the deck. We know that. And the deck is still here. So if you use your line, your visual line, and use the rod through here, you'll see that that means that this 11 is beyond that point. The rod being of whatever rigidity is already trashed the end of this, finished off the rest of this 11. We're going to see a redirect at one point of the forces. Let me, oops. Okay, guys, let me, I'm going to do two things here. I'm going to show you that, and I'm going to show you this. And this will, each one will explain each other. So as we look in here, this is the floor, the decking. This is not across the full decking. Do not get confused. That comes all the way out to the decking. It's only like a blister. It comes right down the middle of the deck. These will be our number 11. This will be our number 12. This is now its shape, if you will. This is about roughly, it's not the scale, but this is giving you an idea that it has this cutout. This is 10 inches. That's the balance of that, which is way out of scale. It should be a lot smaller. I should have this, I think it's like 2 feet and some change. So it should be like 1'2" or something like that. So you can see that's not really proportional. Neither is this, but there's a but part. I can still use it. So let me get over here. Let me shake it, make sure I've got enough inside there. So I just drew it on the piece of styrofoam and hung it up for you. That's the way I do things. Here is post-tension bar number A. Let me make sure I can see that as I'm talking to you. Okay, good. Here's A. A goes all the way up this structure into the blister bar. B does the same thing. These are not cables. These are steel rods. 1 3/4 inch with a ductwork, I think, of 2 inch. It might be 2.5. That's kind of not too relevant yet because I don't need it. So now I just don't need to know it just yet unless I count the voids to make this weaker, which they don't show that in the deductions. They do deductions on the OSHA report, and everyone else in these other forums are just saying, that doesn't count, that doesn't count. This will be a deduction in the strength of this if it was to move laterally. You have to deduct the pockets as they cross the base of the deck here. The base of the deck is where everyone is implying that this slid. Well, let's just jump right to the video. The video does not show this sliding. In fact, it shows the top going outwards like this, kicking over this direction. We're going to watch it kick over. Watch it. It's going to go this direction, not the bottom kicking out. Watch right here. See the failure there, and now she's kicked back in already. Bottom's coming towards us, not away. That's because the post-tension rods are still part of this program. It's being pulled in, kneecapped in a reverse direction, if you will, being pulled by a string. And that string is the number one having a pulling effect as this pulls down because the forces are redirect. And the bottom is stationary. I'm going to show this with, well, I hope to show it with cabling. I'm going to do I'm going to add a few clips here. But why would it just bend over? Well, because it was anchored at the base when this started failing. The failure is out here. This is where it fails, here and here approximately. How do we get the forces out there to make it fail here? Is that, well, let's talk about shear first. So, just in typical, this deck, the shear point weakness would be here where the two planes meet. But this is resolved, I think, in the post-tensioning. The compression and the tensioning of the cables resolve it where you won't get this shear. And yes, everyone's, so I'm being facetious, brilliant about they don't have enough development of shear links, stirrups, if you will. Talking about the design to prove that obviously Denny Payton, Linda Figg, and their engineers or system got it right. So when we see this bridge fail, this one is way out here. It's nowhere near nowhere near this area here. And this has the most loads on it. This doesn't fail with that design. So I don't think that that's the issue, because it doesn't have development, and that allowed sliding of number 11 into 12, kicking it out. Again, then they show, well, wait a minute. Then they show the back of 12. Let me make sure if I got this right. So they show the, I'm going to pause it and do a quick, no, I won't. No, I won't. I'll do this live. I'll do this live. Then they show the back of 12 that looks like, that looks like this. I'm going to show you a little bit differently the back of 12. A little differently. I'm going to help you visualize, and other people with this group think. Get rid of their group think. That's a load. The level is a load. And make sure that you can see that. I can't really tell myself. Yeah, okay. So the level is a load. When they detensioned, yes, when they detensioned number 11, this outside canopy, the canopy has a column, number 12, that is load bearing. That load transferred to the back of, what I call it, in this perspective, the back of the girder. D through 6. This would be D1, and that's D1. When they released the clamping force of the back of this member onto the bridge, that held it on the bridge like that, that was this clamping force down B only. A was inside the deck, so it didn't participate in clamping force. The clamping force, it didn't participate in directly holding 12 onto the deck. When they released that, when they released the clamping force, that little bit of energy that was inside 12, and I say little bit because they detensioned, they didn't undo fully the bar. I think, and they did not grout here. This is the issue about grout. So this is a shim, guys. This will be grouting, if you will. Let me do that for you. Grouting would have stopped that. Let me get you zoomed in a little bit. Well, I think that's plenty. Maybe not. So grouting would have stopped that from falling down. And it's going to be a little hard for me to turn this, right? Let me zoom in a bit. So grouting would have stopped this from falling down. We see that in the OSHA video images where this is 4 inches on one side, 4.5, almost 5, and over here it's 3. And some change. So we had this whole member. To get this to twist, well, the whole bridge didn't twist. What happened when we released the load there, this sheared. This load came down and sheared. As we know in the OSHA images, there's no reinforcement inside this pocket. This created a shear of the dead loads like that. I'm just going to drop that level again to show you, like that. That's the direction of this, and as you can see, that's shear. This is not the video out. Bear with me. So now you see the way shear works, and I gave you guys a beautiful video from this doctor, that PhD doctor of engineering. He let me share his video, and I shared it with you guys the other day, showing you shear. Now this is the shear that everyone's stating has happened right here. But then they discount the bars, both of them, any stirrups that were in there. The dead load of this, they discount that. That's not even counted. And magically, they don't account for how this elongated to cause this pushing movement. You see this level I have here? Now it's here. It's got forces on it by the way of the bridge. That's in a downward force, if you will. But since it's redirecting, and without what they call the profile of quarter-inch concrete, they're claiming that it slid. That it slid. See how it happens when I slide, though? To slide this even a little bit. To slide it even a little bit. What happens to the top? It becomes out of line. If it becomes out of line, that means we got a failure up here. Also, there is nobody identifying a failure at the top node. To move, that would be to separate it on number 11. Magically, it would lose its forces at that point. And once it separates, it no longer has forces. It's broken. It's tension. It's in tension at that point, and it doesn't have the capacity to push anymore. So we don't even see buckling in this member. But what would do it all? Again, you release the post-tensioning rods A and B, but you leave them on taut, just with your hands. You back them out. When they did that, that dropped down into that grout area, which we know now has been measured. It presented itself the first day as small, very small cracks, and I'm going to show you it down below on my foam board. Very small cracks right about here. Also noteworthy is on 228, I believe it's 228. So I find this kind of confusing. Did they remove all the formwork before they post-tension, or did they post-tension and then remove the formwork, or a combination of both? I'd like to get to the bottom of that also. Can't find any data on that specifically. When they post-tension this, and you guys know about my other video that the issue is that they took forces off the bridge when they post-tension 2 and 11, and then they continue posting tension everything else. And at the end, when they put the structure in, they removed the tension off of 2 and 11. That tension was recaptured, I'm calling it, back into the bridge. That tension they took off of it, that weight, that was directed back down to here into the, let's consider this an abutment. It recaptured it back into the structure, which exhibited itself in the breaks we see over the next 3-4 days. In fact, if this B wasn't in there, I say in fact, if B was not in there at that point, if they'd have just unscrewed it, B would have, I think, would have collapsed. When I say in fact and think, that's not the same, is it? So I have to adjust my statement. So, but I still want to say in fact, yeah. So if you were to continue to pull this off, I see that the load path would have continued down, and in fact, I guess I have to say it, would have stopped there. That would have also just destroyed this structural, the structural load path. What it does is, let me zoom up. Let me zoom up for you. I mean, zoom out and tilt up. So what it does by dropping this by 4 inches, let's call it, or dropping it by 3 or 4 inches is failure. But 2 inches, just dropping it, well, whatever inches it was, we don't know a baseline of how tall these shims are. Although I could look them up and figure out the real true drop. If this has to, I have to know that this is in plane. Though I have to know the shims are, say, I didn't look at the shims, 2.5 inches, and then I see that, and they're bigger than that. So let's call it 6-inch shims, and I see a 4-inch drop here. That means the back of this dropped 2 inches. That means the shear on the bottom of this rotated this column like this. Watch this. And this is the way I see it. Well, I see it actually this way. We see it this way and a shift over, as I showed you in the previous videos, at the base on this side. I think they call this the northwest side, and this would be the east. So I'm going to do this as east, and I'm going to do this as west. So then and this is north. So this is exaggeration, but it looks similar to that. That's a rotation that took place. This explains why it's lower down here, higher up here using the tape measure. This is after post-tensioning release. It no longer had the clamp force. This is over many days, creep also. So it did a rotation like that column. But this shows, this is what shear looks like. Now, if that's what shear looks like from this position, you guys can clearly understand the failure there, especially looking at the other video. We just turn the direction of the shear path, right? And if we do that, we have we have a couple of versions of how the shear was supposed to take place. FDOT shows the shear plane up here. OSHA shows the shear plane, I think, down here. Also with the other forms, they're showing the shear plane down here. FDOT has it up here that it would create the effect. Let's pick them both if you like. That's the contact point in there. I would argue that the redirect, I would have to do it like this. I would go straight because these are also forces. I put it down here, and the load does have, it's multi-directional. It still has a downward force, right? In theory, it has a downward force, not in theory, but I'm not part of that theory, but I'm going to go with it. Because once you release this became in tension. I don't have it having, besides this dead load, participating in this joint. I have all the loads coming out the 10. But let's just put the loads on it. Well, it's kicking out, right? It's being pulled in that direction, theoretically, kept in that direction. But this would put the base, not that little chamfer, but it would put it like this, back down to this side. And then where it crosses the plane here, it puts it here. And so I'm going out in a 45 there. This is where the shear factors are inside here. Now, with the downward force. Now, if they got to go on sliding, as they want to do also, then we do the same thing. It's now on the deck, and at the point it hits the 12 column, the same thing happens again. It goes out on the 45. The 45 looks like this. Sort of in line with the B, number 2 on the post-tension rod. And then off of that corner, if it's meeting there, it's going here. Into number 12's column. So you'd see a crack where? Up here somewhere. Don't get excited, there is a crack up there somewhere. That's during the braking. That's not during, it's when the bridge does a force like this. When it does this, kicking over, that's this brake. And then it's going to come back the other direction because it's tied to post-tension cables at the top. So don't get excited about this one little break up there. I'm even going to account for a few things, but I think I'm going to do another video. I have another model I'm working on with the rods in it to show you that. Well, let me see if I can explain it to you. As this is collapsing, so just use, we're going to watch this, we're going to watch number 12 go this direction in the video, right? What happens to that with that cable? Pretty much it's okay at this point. It's doing redirect when it's coming back around. But now the cable is kind of slack. So here's the cable. This column was, once it did that, it blew off the blister bar. It did not cause failure up to here yet. So the failure of number 11, we apparently see the failure way up to here on number 11. We see material missing from the concrete. I don't get that short of two things. One, we have what? We've got failure already in this, as OSHA shows, inside. It cracks all the way up here. It's going to be very easy to cause the rest of that just to peel off and go off into space. We have an anchor point that is loose and sitting on top of the pier at the time of images show up. This anchor is here. That's B. So B only holds on only for a moment to just finish off this. The cable, remember, it's a 1 3/4 inch steel rod. It's beautiful, not called a cable. It has the ability to finish off that just by its dead load of the rest of this structure as it comes down. So this is not even participating. I think it released its forces dramatically once the 280 kips, or whatever it might have been, the 280,000 pounds of force. Remember, this is a reclamp. So this broke free, it dropped down whatever amount of inches. They then attempted to put this, they claimed that the forces were put back on, 280 kips or something like that, 256 kips, 288 kips, whatever it might be. But this doesn't, all those cracks, they just don't go back together. This is not opening a book and closing a book. There's concrete there. It doesn't just blend back in. And we still have it 4 inches down. This doesn't have the ability to jack up the end of a few inches down. I don't know the inches exactly. So a few, we have a settlement here. This only has the ability to clamp again, but not raise. It's not like it was designed to be a sliding joint where you can release and pull back, release and pull back. This was a failure in shear, and now they're trying to put a shear brake back together. I just stepped on my model. You're trying to put a shear brake back together, and it's cat's out the bag. You can't put it back together. Let's talk about the confidence of why perhaps Denny Pate would not have saw this as an issue. And I know I'm attacking a couple of my own viewers, which is stupid, right? You would think, but I'm going to share the data. I don't like groupthink, and I don't like treading lightly. So I don't do. Do I tread lightly, guys? So anyway, sometimes I do. So now, but I still get to my point. So we have the. I'm going to take a little liberty here. That's the outside, and here's the ductwork, and here is the post-tension bar, the tensioning through here. This creates that compression that stops deflection in a deck. Now, I think that it was theoretical, as we know, because it's never been done. The amount of compression, the amount of strands, and the compressive forces to keep this from deflecting. As Linda Fig said, it was all going to be under compression. But the wild card, again, is this 2 and 11. Clearly, they didn't want to make that bridge fail. Clearly, they didn't see that detensioning 11 would create such drama. And number 2. And that's because 12 sits partially on the deck, was designed with an abutment on it. And if you guys remember my first videos, this should not have been done. Detensioning should not have been done until the bridge was complete, as per the first plans. But as of March 6th, I believe Denny Pate, per OSHA's statement, allowed detensioning to take place before the bridge was complete. Obviously, he only thought, as FDOT stated, during movement, this will be needed. But it drives me crazy that he put it in there way ahead of, way in a cycle, way ahead. He did D1s, and then C2s in the Canopy, and then he went to 2 and 11. And as the BPI, which represents FIU, so FIU can't be ignorant about it, claim ignorance, yeah, I'm in there. When this was tensioned, when they put compression on this, when I say that, when they put compression on it, when they tension it, by elongating it, but it actually creates a clamping force inside this member. Clamping force also in the canopy, and let me make sure you guys can see it, in the canopy, the blister bar, and the deck get clamped together. But B also clamps on 12. It clamps on 12. If that was his intent, to hold 12 onto the deck, then why would you ever release it? So let's go to, well, clearly it's hanging over the deck. Clearly it's got a blister bar, a blister on it, I'm using their terminology, a blister on it outside of here. Why did you detension it? So, when it was tensioned, compression put on it, the BP CEI, representing FIU, stated that he thinks that they believe it temporarily place tension at number 10. Now those are very small cracks in here. There's a butt part, guys. Remember, these are rods inside here still, steel rods of the magnitude of 4, I believe, inside this member. And my hands are getting dirtier by the moment. And they're coming through this blister bar. They've already been turned in to some degree. I'm sure this was not, these nuts were on top of these guys. They didn't just not put the plates on. This was already tensioning now. The plates are on, the nuts are snug. So when you only see the small amount of tension here, you have to realize that that means that this thing is holding up the base at this point. This brings me to friction and formwork. Forms would have been in here, and they would have to deduct for the friction of the formwork and all of their post-tensioning, which was 175 feet of formwork and so many different factors, including down to the ground. So the friction of the ground surface as it relates to the base of here. The friction of this guy also. It is some, and you're saying, well, it's solid. There is no friction experienced out there. All right, its post-tension is an odd duct. It's a very odd duct. It's a very odd duct with the friction and things like that. All right. So friction still has to be considered. And with that said, let's go to the friction of the joints again. So you're pulling this one down, tensioning this one. All of a sudden you see cracks here. That signifies that putting post-tensioning on this one actually created a dropping or a movement between this one and this guy, separating like this. Separating. These are parallel with the deck. If it was like in this direction, the crack was this direction, I would say this created a cross force that put tension in the member, and the cracks would look like a reinforcement pushing against the concrete, creating tension, following the tension line. This is an opening. These are parallel. They're opening. I love cracks, and this is how I visualize how these cracks were created. I create thousands of cracks every year just to look at them. I mean, I'll hit it with a sledgehammer. You guys see my videos. Those, what you didn't see in those videos when I'm doing sledgehammers, me stopping sometimes, putting pieces aside, knowing what I'm looking at. I turn this, you know, I even think about impact of the sledgehammer, and I only want to run all the forces down to the very tip. I quite often get guys that break concrete telling me they don't know how to use the hammer. They don't know how to use forces to concentrate the forces. And that's why I make concrete look so easy. I always break it over reinforcement if I know, once I locate the reinforcement. That's the weakest point. This is why I tell you that. Because it's hollow, the metal works in your favor to create a resonance, to create a crack. We have over here, and before detensioning, these cracks showing up after movement. Very small though, not large. And these are the cracks I did a video on initially. So this part I'm biased on because it supports my statement. As the one guy who attacked me said, you have confirmation bias about F dot and something else. Now I know my biases, and I have bias against this would be, and I share my biases because I'll tell you when I came about it, and I also tell you, well, I tell you as I speak to you, and I can almost always spot my biases. I don't know when I've not been able to spot them. So I mentioned this a long time ago. So therefore, that would be sort of a confirmation bias by now bringing it back to this. So it's up to you to figure it out. But I'll take care of that in the cardboard down below. To create this opening here, right here between the chamfer, an opening, you're going to have to make this deck longer, keeping this side on this side of the deck and the base on that side of the deck. Is that possible with post-tensioning? So let's eliminate it. You can't make it longer this way just by pulling it apart. There's no jackhammer in there. Can you add post-tensioning on here? And the conflict between the two of these, the chamfer and the deck, would create a shear like this and cause a crack. Yeah, you could do that, but you'd also have to show me movement and compression, and possibly it would be compressive break here. I see that when I investigated that crack initially, it's a shear crack, but more like a flexural crack, and a flexural crack. It's upside down. I'll show it to you. I'll show it to you in the cardboard. But when this dips down, you also want to see possibly this dip up. You know, with this going down, you want to see some reaction here. We'll get to that. But remember, you got post-tension bars in there at this time, and they're still tension. These are not detension at the time we get to see these cracks here. All you have to do is go down here, and this deck was creeping. It was already had creep in it, and it's identified as this. What kept this so an assumption, and this would be biased. I think the assumption, this is biased. I think the assumption is by Denny Pate and all the other engineers that look at this, and double dip I call it. I said I'd do a video on double dip for, I don't know, it was DOS or somebody I said that. About double dipping. You tell me that everything's got to be in compression, Linda Fig. I totally get it, totally love the idea behind it. But then you take the reinforcement, the load off of this. Because I guess you don't want to overload it, or if it was only for transportation, you think it causes deflection, whatever it may be. You maybe think that's how you're going to stop this crack, that you have excessive forces here, or you misunderstood what you're looking at. The cracks, you misevaluated this very importantly. Perhaps they went with the detension because of that slight crack, but it was done the day of. So this was already decided that these tension cracks up here were moot, not an issue. So the double dipping part is you're treating it like a truss, because you're telling me the loads are transferring down here. That doesn't make sense. You're double dipping because you said everything had to be compression, and now you're telling me you've got some deflection going on, and that puts us in compression. That it puts it in compression at that point. Well, then I say right then, you should not have any deflection going on if everything's supposed to be in compression. The theory behind your structure, well, I understand the theory better than you. I stand, not the reason, but I 100%, I'm solid on that one. I'm not, that's an inclusive file for me. That I get the total thing. You can't have deflection then. The moment you have deflection, you have compression and tension. But if you can keep everything rigid, basically, you're putting a 10-pound weight on a 2x8 piece of steel that's standing on top of up here with no shims. It's flat. It goes out. There's no deflection if you put a load on it, so you don't have to worry about anything. That's the confidence that you would get from the tendons, having no deflection in the deck. That it doesn't matter if you got cracks here or anything else, because you've overloaded you've overcalculated how much compression you need to handle the entire bridge weight, plus the 16-inch pipes that apparently might have been 1 3/4 inch thick walled, which is some mega huge weight that was going to go on top of these guys. So these cracks here, they're nothing. They're mute. You know, there's nothing to them. So all these cracks would be like, no big deal, except for, again, the load path is where they messed up. When this became loose and dropped down right here, and it dropped down, it created this shear back here, which shows it's not structurally sound now. All the engineers should have known what they were looking at that point. But it turns out most engineers these days only know theoretically what's going on, and they don't know how to evaluate failures because they don't go to look at failures enough. They only go to look at their successes. And that's the problem. You know, you need somebody on there possibly that can evaluate failures, and that was part of the plans, as I understood, but that didn't work out. So releasing this created the tension here, which we know now dropped down. It's not a freebie. You can't drop this down for free at any amount. If you do that, you're dropping down the canopy. If you drop down the canopy just that much, you've now changed the load transfer of this whole structure. Not this going down here. You changed it. And we know it came down 10 because of the video. It breaks here, resolves itself here, and approximately right behind the node here, which again shows Denny Pate, and Denny Pate, if he's the one that shows how awesome he really did do each one of these nodal things. It's only a small screw up that caused the lives, and that's this 2 and 11, which FDOT told him to put in. If he didn't put it in there, Denny Pate, this thing probably would have failed when they load tested it, because this would have still been part of the same configuration. And as far as I know, I looked at it, it looked like the same configuration with no rods in it. So it would have taken the loads. It would have, well, no, it depends how they had it over there too. Did they have this fully shimmed over there, fully shimmed in the staging area? And that makes a huge difference right there. It's fully shimmed over there, which since it was in form work, I would guess it was. Okay, let me show you the cardboard down on the floor. And I'm going to have to take a moment to work this out for you. So this is a flooring they had on here from a long time ago. I've been taking it up, working on it. This whole floor's got to come up. It's a nightmare. This house is over 100 years old, and they sort of just do what they wanted to do. So this is sort of what we're looking at. So this should be the floor, where the post-tension rods are, the longitudinal tension cables are coming across. This is the deck. This will be 12, and this will be 11. This is the rod going through 12, sticking over here inside of this guy. Let me back that out for you a little bit. I need the top of it. So far, so good, right? Okay. So let's just look at this. I'll put a hairpin in here, if you will. Not from my head, obviously. So I can get some flexibility. Let's just get to your crack here first. This is connected to the deck. Watch what happens when I dip down here approximately, down to 10 area. It's going to dip down just a hair bit. Watch what happens to the foam. Just dipping it a little bit. See the breakage? You see your line break? This is during creep. So it had creep. This was connected to the deck. This was connected to the deck. And when you do that slight break like that, it gets you an opening that looks like, I'm going to keep this, looks like that. That's your crack. Oh yeah, that's not working. I need to zoom in. And possibly go above it. Zoom out a bit. Okay. So where are we here? Right. So this is the way it looks like. It's clamped on with this clamp here. This is where we see the failure on the end of the deck. There's no apparently all the reinforcement straight up and down here, which they didn't deduct for. That was still inside 12. That would have stopped the lateral movement also. But no deduction. None of the forms are doing deductions for that reinforcement going there. In fact, they're just pointing out confirmation bias that it's a hollow and it can just slide out now, magically slide out. And yet they're not accounting for everything, including this first crack. This first crack is very important. This is where the bridge dipped down just a little bit. Watch it again. It opens at the top. So it's concrete. It's still connected at the deck here. And as this creeps down, that's your opening. I'm exaggerating now. That's your opening. That's how you explain that little chamfer's opening initially. Now later on, we got 4 or 5 days of creep going on. Let's advance it. So we no longer have the clamp force on this one. This that rotation I showed you. We got a separation right here on the deck, so it rotated a little bit on top of the deck as it caused a tension shear breaks in the back of the girder system at that point when you're looking from the rear. The loads are on the back. This is totally unfair for me to do this. I should have had it, melted more of this off for fairness. So it looks, way over here. It's like that. So I've got it look like it's almost balanced on the deck. But let's go with it. So remember the top of this, also, you can't see it. The top of it, let me show you, is also a weird joint. It's a scarf joint or something like that. That's how it's holding onto the canopy up there. And you're going to see when I bend it, when I push this base out. Okay, I'll just do it. Zoom out a little bit. And, okay. So let's put it back together. There we go. So it's clamped together now. Great. Boom. They released the clamp force. Remember, they released the clamp force. They don't undo the nut. So this it drops down, it cracked like hell. That's your shear of the load there. The loads cause all that shear. Not they released the clamp force and it slid this way. It's the shear. It would look like I told you, like you got a few choices you can choose from there. The patterns. So the pattern would look like initially like this. So that's the base. If you're going to transfer loads like that, it could be out here. You could possibly pick where they stops at 12. And this would be on the shear. The brake would be on the decking internally, but you're looking at the side view of it. So internally side view like this. There's nothing that indicates that because we get to look down there. Now this one would be roughly an indicator of that, but we don't have this back here. The failure is way back here. We don't have this one, so that wasn't a path. So the path would go as F dot shows it. It would have been the shear plane is up here. That would look like that on the column, or possibly like this, or like this. It's all over the place, but none of them presented. What did present was the one I showed you, the girder system that's falling down. So now this fall, and I would argue that would be impossible to present based on what's left of this member, plus the sliding of having to go through 2 post-tension bars to do it, to slide it out. Then we have also the video. And then remember, this is going sliding. It's not the same as my shear going out to the side. They still had vertical uprights in here. They do have to go through those vertical uprights. And I'm not sure if there are any stirrups in this location down here. But with mine, the vertical uprights are irrelevant. They're in line with the shear path, so they do not cross it. So they're actually not an issue. My system of failure works. When this falls down just a bit, it shears now. That changed that top up there, and that's the canopy. So this falls down, but it's only a node. Remember, it doesn't go to full deck. It only drops down this much. That's enough to cause a deflection in the deck, which puts the loads down 10. And then with just a matter of elongating these cables, they're just sitting there, waiting, creeping, waiting to fail. Let's show the action again. I'm going to put a load here where my hand is. It's going to creep it down more now because this is already failed. It's already sheared. They got the bars now holding it on just because the nuts are on it. The bars, 2 of them, but more so this B. This whole thing's being held on by B because A is still in the deck. It's not really performing yet. As far as I know, I think all the loads are just down there. So now we have what they said, shim back here. shim it up, you know, the meeting. Make this flush. Now, I took a little liberty here to make it stand out, but this was actually even with the bottom of the deck, the way down here at the bottom, it would just be, you know, that much grouting, the grounded up. So now, I'm going to take a little, I'm going to push down on my hand here, and this will be, try to square it back up for you, because these gaps aren't representing, I don't think, okay, we go. So watch now, push down. Go, I got a little, got my own friction going on. So I'm going to push down. We get a gap again, we get gaps again. This has a rod in it. So the creep in this one has the effect of making this rod increase clamping power as this creeps down. This rod, once it's retension at 280 kips, let's call it, 280 whatever, as this is creeping down, that puts tension in this one and this one, which creates even more force at the canopy node, which of course is going down 10 as you're pushing out. So 10, watch B right here, as I do this, creates more tension inside, I'm sorry, 10, B, puts more tension in there. This increases its amplitudes up, its clamp force. This is already cracked and destroyed, and it just blasts through. The collapse starts happening. It just blasts through. But I'm going to end the video with this. It's sheared. Inside there, we see that this is still existing. This is the floor, the deck. And right about here, let's go with that. Here's the other bar going through there that was there one time. This concrete's already failed though, because I showed you the shear plane. We see it in the images too. When you put that back together with this clamp force, all that broken concrete in there that was broken, it's now, I believe, acting like a shim. Whatever shapes they are, they act like a shim, and the clamping force helps this thing disintegrate right here. It doesn't need much. It does not need much to cause failure in B. It only has that blister to make it fail. It only has to fail at that blister. Here's a pipe. The drain pipe's right above it. Not all. This doesn't count. This area doesn't count. It's below the drain pipe. It's only this area right here that needs to fail by clamp force. This area is the critical area that's holding up 12 from continuing its shearing downwards. That clamp force that was created in B doing the reclamping or reclamping started the failure. If I missed anything, just ask me and I'll put it back in the new video. I'll put it back in the comments. But that's